Okay, so it's my pleasure to welcome Professor Biswajyoti Saha from IIT Delhi, and he is going to tell us about multi-zeta functions, analytic and arithmetic theory.
Thank you, and it's really a matter of pleasure for me. And 10 years back, when IMSc was celebrating IMSc 50, I was just a first-year graduate student here. So it's really a very nice homecoming. And so today I'll be talking about multiple zeta functions, analytic and its arithmetic theory. So there will be probably you will be seeing some numbers which you can perhaps relate to your field, especially let's say in physics. But I'll not be talking about those things. I'll be talking mostly mathematical theory. So let's quickly begin. I don't know. Yeah. Okay. So of course it's kind of customary for us to start with Riemann zeta function, and then it's defined on this complex half plane, right half plane, by this infinite series expression, which converges absolutely on compact subsets of this open set. So therefore it defines a holomorphic function. Now it's not very technical, but if we just use partial summation technique, this function can be extended to the complex right plane real part of S positive, where the function looks something like this. Yeah. And this part should tell you that that has a simple pole at 1 with residue 1, and this improper integral of course converges whenever real part of S is positive. Okay, and of course that's the celebrated work of Riemann, which says that this Riemann zeta function extends to the whole complex plane as a meromorphic function with just a simple pole at 1 with residue 1, and here goes the celebrated functional equation with it. Okay, so although this particular function bears name of Riemann, it's Euler who was first studying this function, and all of us probably know about this famous Basel problem, which was about evaluating zeta of 2, that is harmonic sum 1 over n square, in terms of known constants. Okay, so we have something more general that in for any even any integer n, zeta of 2n is rational multiple of pi power 2n. So this rational number is not so important, but it's just pi power 2n that we get over here. So of course one knows now that pi is transcendental, so therefore these numbers are transcendental, and in fact they are Q linearly independent. Okay, so once we have this nice structure about the even zeta values, it's natural to inquire about the odd zeta values, and as it turns out that all these odd zeta values, it's a folklore that these are new numbers. So what do I mean by new? So if we see these even zeta values, they are just kind of pi, so effectively it's pi. But these odd zeta values are believed to be algebraically independent with these with pi, and all of them are kind of algebraically independent, so they are kind of new numbers. Okay, so now it's not clear why Euler came up with this highlighted identity, but somehow let's imagine that he was trying to multiply or two zeta values, and he was trying to see what it comes out to be. So it seems like since we are in the domain of convergence, we can break our series, in whichever way we like, and we end up having these kind of nested sums, and of course this is the Riemann zeta function. So this tells something very interesting. It tells us that if we are to look for polynomial relations among zeta values, then it will perhaps be easier to read rather it as a linear relation among these numbers. Okay, and we can do some linear algebra that might be helpful. Okay, so that brings us to this setup of multiple zeta functions. I'll go through quickly. Here I need a technical open subset of C power R, and we can define this multiple zeta function as a similar nested sum over where the sum is over these indices, and it's an infinite sum, but nevertheless this will converge uniformly on compact subsets, and again it will therefore be holomorphic on this particular open subset. Okay, so once you take these new numbers, you start seeing more relations, and this one is a classic. So that goes back to Euler, which says that zeta of 3 is zeta of 2 comma 1. Okay, now I am told that every talk should have a proof, so let's see a quick proof. So here I am taking one particular sum S, which is 1 upon mn and m plus n. So just AMGM inequality will tell us that this exponent of m and n in the denominator is at least 3 by 2. So therefore I can do whatever random operations or manipulations that I would like to do, and therefore if I do it carefully enough, in one hand it becomes zeta 3 plus zeta 21, on the other hand it's twice zeta 21, so therefore zeta 3 is equal to zeta 21. Okay, so therefore this number seems interesting, but although they somehow they got lost into the literature, and they only came back due to two papers of Hopman and Zagier in 1992. So this subject is fairly new, around 30 years old. So let's go to the next thing. So of course I was talking about the Riemann zeta function, and I said about the analytic theory. So I will again quickly go through the analytic theory of multiple zeta functions. So we also have a kind of extension. We had seen that the multiple zeta function was defined only in a subset of C power R, and one can still nevertheless extend it, but the extension is not so easy in the sense we do not have, let's say, functional equation of the Riemann type. Okay, but nevertheless it says something interesting. It says that I have certain simple polar hyperplanes which I need to explain. I will do it in a future slide, and these hyperplanes are kind of listed. So it's S1 equal to 1, like for Riemann zeta function S equal to 1, and then S1 plus S2 equal to 2, S1 plus S2 equal to 1, and so on and so forth. And this set Z less than or equal to I means set of all integers which are less than or equal to I. So there is another major difference, is that now I am going to have infinitely many hyperplanes where I might be having some problems where I can't have my function to be holomorphic. So that's the first theorem from Zhao, and I think soon after there was a theorem by Akiyama, Egami and Tanigawa which kind of said the same thing, except that it said that okay, this list contains some of the redundant hyperplanes, so one needs to get rid of those ones, and these are the ones highlighted in red. These are the ones, if you throw them away, then you take any point on the complex plane, then this function will be holomorphic there, which are not lying in these hyperplanes. Okay, so now I have not explained many things over here. This possible, this simple, what do I mean by simple, and polar hyperplanes, what do I mean by polar hyperplanes. We are talking about functions of several complex variables, so this is more technical. So therefore what I would rather like to do is that I would like to give you local expression of these functions. Once I give you local expressions of these functions, this will be absolutely clear what is our function, what is the part which is kind of problematic for these points, and we will see it more clearly. Okay, and as I said, of course there is no functional equation like Riemann type, so it's of course of another interest that whether do we know how to assign values of our function, this multiple zeta function, outside the domain of convergence in some way or not. So that will be quite clear once we see local expressions. Okay, so local expression means what? If I think of Riemann zeta function around 1, if I want to ask for a local expression, it will just be Laura expansion. Now again we are in trouble because we are doing functions of several variables, we don't have any recipe to write Laura expansion, or there is no concept of as such Laura expansion that way. So how do we do that? So that's the aim for the next slide. So of course if I have a point which is in the domain of convergence, I can just write Taylor expansion, boom, we are done. Now if we are outside the domain of convergence, what happens? That is the question. Okay, so let's try to see if we have some hints around. If we think of Taylor expansion, then the coefficients are coming from the derivatives, right? That's high school. But if I am outside the domain of convergence, how do I differentiate? What is the function? That itself I do not know. So how do we get around this? So let's go back to the Riemann zeta case, and that brings us to the paper of Stilges. So Stilges did what? Stilges did that. This is of course one variable case, so I can write zeta of s as 1 upon s minus 1, that's the polar part, and we have something which is entire, and that's given by this power series, where these constants, gamma k's, these are called Stilges constants, and they are quite interesting because they are given by this particular expression. So now here I would like to point out one thing. So let us try to see what is going on over here. So this Stilges constant is just I am going to take this partial sum of this infinite series which does not converge at s equal to 1, and I am subtracting some part which is going to go to infinity. So this is a kind of regularization process, and that's again fairly common in various fields, like particularly in physics. So whenever you have something infinite, you try to figure out which is the cause, like what's the cause of making it infinite, you throw that away, take the thing which is remaining. So this is exactly what we are trying, one is trying to do here, and these gamma k's are defined in this way. And if you notice, this guy, this series is coming from taking higher derivatives of the Riemann zeta function. So therefore, what you can treat these gamma k's as, these gamma k's are rather not the derivative at 1, but rather the regularized derivative at 1. Okay, so that's how one can interpret this, and long story short, one can do a similar kind of regularization process for higher variable also. One needs to be a bit careful, as I said, there is already no standard notions of writing Laura expansion, so one has to be a bit careful, but one can do this regularization process for this series with multiple zeta function with it. So once we do that good enough, we get explicit local behavior of our multiple zeta function around any given integer point. So let's take one example, let's take 1, 1. So what do we see? We see that zeta of S1, S2 is 1 upon S1 minus 1, S1 plus S2 minus 2, and again 1 upon S1 minus 1 times a power series, and again a power series of 2 variable. So therefore, now I understand what did I mean by local polar hyperplanes, simple polar hyperplanes. So if I take this point 1, 1, the hyperplanes that were listed there, among those hyperplanes I have 2 of them passing through these points, on which this point is lying. So those hyperplanes are S1 equal to 1 and S1 plus S2 equal to 2. Lo and behold, if I just multiply this function by S1 minus 1 times S1 plus S2 minus 2, I get something which is holomorphic, and that's evident from this expression. So I really understand what I really mean by simple polar hyperplanes. I just need to multiply by single factors of these equations of the polar hyperplanes, and I will get something which is holomorphic. And I can do something, I can give few more examples. Let's take the point 0, 0. Here the local expression is a bit more tricky, but nevertheless again I have some power series and some rational functions over here. So again, if I clear out the denominator, so here the only hyperplane that is interesting is S1 plus S2 equal to 0. If I multiply it out, I will get something which is holomorphic around 0, 0. Okay, that's the point. And here is one more around the point 0, 1, minus 1. So here the function is actually holomorphic. So you do not see any denominator over here. Everything is holomorphic. That's good. And that is precisely which was predicted if we go back by Akiyama, Egami, and Tanikawa, that these are the hyperplanes which you should throw away. So for instance, you should throw away S1 plus S2 equal to minus 1. So therefore, clearly if I take this particular point 0, minus 1, it's this problem is not a problematic point. It's a fairly nice point. Okay, so I think yeah, I'm kind of in the midway. So we will go to the next half of my talk, which is the arithmetic theory. Okay, so we started doing the same thing for Riemann zeta function as well. We started looking at the values. So here also let's do that, and here the special values will be zeta a1 to ar. For the convergence condition, I just need to take this a1 to be bigger than or equal to 2, and all other ai's I take them to be positive. That's good enough. Okay, and once we take these sums, we need to have an invariant attached to them. So that's the weight, and the weight is the sum of the indices. And once we have this setup, one can define, like as I said, I would like to do linear algebra. So we can actually define certain vector spaces over Q, let's say. So the weight 0 space is just Q, weight 1 space is 0, and weight K space is space generated by all the multiple zeta values of weight K. Okay, so that's my space ZK. And again, as I said, if we, since we have, have made this setup, we are going to see more and more relations. So what are few relations? Few relations are like zeta 4 equal to zeta 2 1 1, zeta 4 equal to zeta 2 2 plus zeta 3 1, zeta 4 equal to 4 times zeta 3 1. So in fact, these are all the relations up to weight 4. This one and the previous one which I had, Euler's relation, which I had seen, I had mentioned. So therefore, what it turns out that all these relations, there is one thing common, is that unless I can break my relation into several sub-relations, I will always get relations among zeta values of which is weight preserving. On the left hand side, whatever is my weight, on the right hand side I should be having the same weight. So that brings us to the conjecture, very first conjecture, that's due to Zagier, which says that there is no non-trivial linear relation between multiple zeta values of different weights. So that means if I consider the Q vector space of all multiple zeta values, then that has a direct sum decomposition where the decomposition is based on these weights. Okay. Now that's a very strong statement to make, because for instance, this particular theorem tells us that all the odd zeta values are transcendental, because if they would have satisfied a polynomial relation, then each of the segment, each of the monomial would have been of different weight, and that's not allowed. So this is very powerful. In fact, it's nothing special about odd zeta values. Any multiple zeta value would be transcendental because of this particular conjecture, and of course one should mention that this is way beyond our capacity of proving at this moment. So let's go ahead and we can look at these spaces Zk a bit more carefully. So of course these were generated by weight k multiple zeta values. There are about 2 to the power k minus 2 of them. So these are finite dimensional vector spaces. One asks if we know what are the dimensions. So again Zagier comes to our rescue, and he predicted certain kind of dimension for these spaces. It looks like the recurrence is kind of Fibonacci recurrence, but it's not quite, but okay, kind of similar, and we understand that these are also exponentially growing numbers. Okay, so that's the conjecture, and let's see what's the state of the art. So the first proof towards this conjecture is due to Terasoma and Delin-Goncharov, which says that okay, indeed these are finite dimensional spaces, and these decays are good enough bound, in the sense they are actually upper bound. Okay, so that's nice, but do we know something on the other hand? Okay, so that's the problem that we are going to encounter. So in fact, like life is even, there is some hope, in the sense that Hoffman had predicted a basis for these kind of spaces. Okay, but like I said, this is the point where we are stuck. In fact, even after having identified a possible candidate for basis, Francis Brown's work only gives us that this is a generating set. We still do not have anything about the linear independence. Okay, so that's a very hard problem. So just to tell you that how hard it is, so let's take the weight 5. So here my basis, probable basis, contains two elements, zeta of 2 3 and zeta of 3 2. If I want to say that they are Q linearly independent, it means to say that their ratio is an irrational number. Now any kind of statement of proving certain number is irrational or transcendental is very hard, and these ones are completely out of scope at this moment. Okay, so in fact the situation is so hopeless that the only known values of the dimension of these Zk space, these are ones. So Z3 is one dimensional, Z4 is one dimensional. We still do not have any single known space where the dimension is at least 2. Of course, it is predicted, like 5 is predicted to have dimension for 2, but that's not known. So how do we understand these dimensions better? The way to understand them is to understand source of all possible linear relations. Once we understand that, then we might get an equality in this dimension conjecture. Okay, but again that's a conjecture for by Ihara, Kaneko and Zagier. For the interest of time, I will skip that, and then I will try to just explain for the last couple of minutes an extended setup. So it's natural, whenever we have a problem which we can't solve, we try to extend and see if there are elements coming from something outside which can help us solving this. So what's the extension that I'm proposing, or like we would like to study, is a similar sum, but here the indices are odd. Okay, it's exactly the same sum, indices are odd. So if I take the r equal to 1 case, you see it's just n bigger than equal to 1 to n minus 1 power minus a. And if I add the even terms and subtract, it just comes out to be some rational multiple of zeta values. Well, good. And many of you can identify that this sum is actually a Hurwitz zeta value. So that was fairly simple in case of one dimension or depth 1. But that's not so trivial in case of higher depths. It's a theorem of Murakami which says that indeed the set of multiple zeta values is lying inside the set of multiple t values, which I have taken over here. And do we have analogous predictions for multiple t values? Well, we have a conjecture of Hoffman which says how these dimensions grow. This time it's exactly Fibonacci recurrence, and we know this. So therefore clearly this dimension is expected to be bigger than zk, and in fact we have predicted basis for this thing, and all that is true. All that we have, all these predictions are there. But I would like to end with something which is interesting here. Let's look at the weight 3 space. So weight 3 space, if I write down the basis, it's T21 and T3. So therefore these two numbers, we expect them to be linearly independent, so clearly they are not equal. But these two were equal when we had multiple zeta values. When we treated zeta of 21, it was equal to zeta of 3. But in this case, these two are different. So therefore, although we know how did really zeta 21 became equal to zeta 3, or we know what is the source of this relation, here it seems these two are not equal. So here we are in a kind of a blind spot, in the sense, to the best of my knowledge, we do not know what are the expected source of all relations. Okay. So fine, we have extended our setup, but then we are stuck again. So is there any hope for going ahead? So indeed there is some hope. Okay. So that's my last comment over here. So there seem to exist a weight decreasing derivation on the algebra of multiple t values, which does not exist in the case of multiple zeta values. So what does it say? It says that if we just restrict onto multiple zeta values, we do not see certain maps appearing. Once we extend our setup, we see certain maps appearing. Now what it helps? It helps to distinguish T21 and T3. Why? Because T3 is effectively a zeta value, which was zeta 3 or some multiple of zeta 3. So it helps to distinguish between these two numbers. So this number upon that derivation will not vanish, but this number upon that derivation will vanish. So therefore what happens is that now I get a recipe to say that these two numbers are linearly independent, because one linear map is killing this one and not killing this one. So they can't be rational multiple of each other. So therefore that gives you that this dimension is 2. Remember, in case of the multi-zeta space, we did not even have a single space where the dimension is known to be 2. Of course, here I am not claiming that this is now settled already, but one has reduced this problem of irrationality to finding something which is algebraic. Its derivation is talking about some derivation on this algebra, so it has become an algebra problem rather than an irrationality problem, because any problem with hardcode numbers, that's much more difficult than dealing with some structure object. Okay, so that's the work in progress, getting an explicit expression of this derivation, and hopefully next time I will have something more to report on this. And thank you very much.
Thanks, Biswajyoti,
yes,
and we have a token of appreciation for you.